Ohm's law states that when the physical conditions of a conductor, such as temperature, remains constant, the current flowing through the conductor is directly proportional to the potential difference across the ends of the conductor. Let us now consider a conductor whose ends are connected to a battery such that a potential difference V is applied across it. A current I flows through the conductor. So according to Ohm's law, when the temperature is constant, the current flowing through the conductor is directly proportional to the potential difference applied across its ends. So this is a proportionality relation. All proportionality relations can be equated by a constant. So here the constant of proportionality is 1 divided by R, the reciprocal of R. R is known as the electrical resistance. The value of this constant depends on the length of the conductor, its cross-sectional area, the nature of material, and the temperature. This equation can be written as potential difference divided by electric current is equal to a constant, which is resistance. So V divided by I is equal to R, where R is a constant which depends upon the length of the conductor, its cross-sectional area, the nature of material, and the temperature. From this relation, it is obvious that electric current flowing through a conductor is directly proportional to the potential difference across the ends. So if the potential difference across a conductor is doubled, the current flowing through it also gets doubled. If the potential difference is halved, the current flowing through the conductor also gets halved. And the electric current flowing through the conductor is inversely proportional to the resistance, which means that if resistance is doubled, current becomes half, and if the resistance is made half, the current becomes double. This implies that the electric current, which is the rate of flow of electric charge through a conductor, depends on the potential difference applied across it and the resistance of the conductor. Electric current is constituted by the flow of electrons through the conductor. When electron moves, it collides with other atoms and ions inside the conductor. This collision causes the obstruction to the flow of electrons, which means the opposition to the flow of electric current. The property of the conductor by which it opposes the flow of electric current through it is known as electrical resistance. The resistance of a conductor is expressed as the ratio of potential difference across its ends to the current flowing through it. It is worth mentioning again that the electric resistance of a conductor depends on its length, the thickness or cross-sectional area, the nature of material, and the temperature. The SI unit of resistance is ohm, which is denoted by the alphabet omega. From this equation, we can write 1 ohm is equal to 1 volt divided by 1 ampere. Thus, we can define resistance according to this equation. The resistance of a conductor is equal to 1 ohm when 1 ampere current flows through the conductor if a potential difference of 1 volt is applied across its ends. Also, if the current flowing through the conductor is 1 ampere, then we can say V equal to R. So if I equal to 1, V equal to R. So we can say the resistance of a conductor is numerically equal to the potential difference across its ends when 1 ampere current flows through it. Let us discuss a very simple problem based on Ohm's law. It is given that the potential difference between 2 points of a conductor is 0.1 volt when 2 ampere current flows through it. Find the resistance of the conductor. So this is an easy question. We have to directly substitute So given that the potential difference between 2 points is 0.1 volt and the current flowing through it is 2 ampere. So the resistance will be 0.1 divided by 2, which will be 0.05. So the answer is 0.05 ohm. Let us discuss another problem. An electrical circuit consists of a resistance of 60 ohm connected to a battery of potential difference 24 volt. We have to calculate the current flowing through it, assuming that the connection wires having negligible resistance. So in order to find current, we can make use of the equation from Ohm's law as I is equal to V by R from the same equation. So here the potential difference is given as 24 volt and the resistance is given as 60 ohm. So answer is 24 divided by 60, which is 0.4 ampere. These two problems were quite simple. It was direct substitution in Ohm's law. Let us discuss a step further. In third question, it is given that an electric iron draws a current of 3.4 ampere when connected across a 220 volt supply. Calculate the current drawn by the same electric iron when connected across a 110 volt supply. So the question is to find the current drawn by the electric iron when connected to 110 volt mains. So I is equal to V divided by R. The iron is connected across a source of 110 volt and we have to find the current drawn, but the resistance is not given. But we can find the resistance of the given electric iron from the initial data given. It is given that the iron draws 3.4 ampere of current when connected across 220 volt. From this, we can easily calculate the resistance of the iron. So the electric iron has the resistance given by the same Ohm's law equation. So R is equal to V over I. So R is equal to 220 divided by 3.4, which is equal to 64.7 ohm. Now making use of this value in this given equation, we have I is equal to 110 divided by 64.7, which is equal to 1.7 ampere. So I'll explain the question once again. It was given that an electric iron draws a current of 3.4 ampere when connected across 220 volt main. We have to find the current drawn by the iron from a 110 volt supply mains. So current drawn is potential difference divided by resistance, which is 110 divided by R. The resistance of the electric iron is not given but can be found out by the given hint. So R is equal to V by I, again from Ohm's law. So from the given data we found the resistance and substituted here to get the required answer. Now the graph between V and I. A graph drawn between the potential difference across the conductor and the current flowing through it is known as the VI graph, where the potential difference is always drawn on x-axis and the current on y-axis. Since the potential difference and current are directly proportional to each other, the graph will be a straight line passing through the origin. This can be easily drawn by varying the potential difference across a conductor and noting each current value corresponding to the potential difference. Since V and I are proportional, we obtain a straight line graph. So from practical analysis, we obtain a straight graph and can conclude that V is proportional to I and Ohm's law is valid. Those substances which obey Ohm's law are known as ohmic. All metallic conductors obey Ohm's law and are ohmic, whereas semiconductor devices does not obey Ohm's law. So they are known as non-ohmic. The graph of potential difference versus current for non-ohmic devices will not be a straight line.